Welcome back. In this lesson, we're going to look at one of the most important and critical rules to chemistry, and that is called the octet rule. So an octet is anything made up of 8, and conceptually, we're going to imagine that the electrons, which blur around the nucleus in a cloud, actually are in various spaces, in various distances, I guess, away from the nucleus. We can think of a short or a close shell as containing 2 electrons, and then the next shell as containing 8, and then there's a mathematical formula that you would follow to find out how many electrons are in each subsequent shell. The very outside shell of electrons is called the valence shell, and the valence shell would be like a wedding veil is on the outside of the bride's face. So there's something on the outside. So the valence shell of electrons, we're going to see, is extremely important in terms of whether 2 atoms will interact chemically with each other. What we're going to see is that fundamentally there is either a stealing of electrons, one atom will steal the electrons from the valence shell of another, or there's going to be a sharing of electrons where 2 atoms will share their valence electrons, or you will have a situation where the valence electrons are delocalized from each atom and is free to move on the surface of the entire metal in this case. Okay, so we're going to see that the outside electrons deal with differently, and they're going to be called the octet rule. So first we need to think about why then an atom would bond with another atom to start with. Why don't they just leave each other alone? The best example that I can give of this is by an analogy. If you think of a boulder at the top of a cliff that's going to fall off that cliff, my first question would be, how far does the boulder fall? So, silly question, I think, but if you were to have a boulder at the top of a cliff, where does the boulder land? Maybe that's a different way to say it. Where would the boulder finish up? When would it stop rolling? It'll keep rolling until what? That's the idea. So if I have a boulder and it's falling off, it's going to start keeping on falling as long as there is nothing underneath it to allow it to stop. It's possible that it could stop there. Okay, that's enough of a ledge, I guess, for that boulder to stop. It might not, and it would continue falling. Eventually it gets to the bottom of the hill and stops. It could roll, but then eventually it's going to stop rolling. So the boulder falls because it's unstable. At the very top of the cliff, it was fine as long as it was. As soon as it was dislodged and it becomes unstable, it starts to roll, it starts to fall, and it continues to fall, and while it's unstable. As soon as it gets to a stable place, for instance, this ledge, it's possible that it could stop. Okay, if there is enough stability there that it actually could land and not move any further, then that boulder would stop right there on the ledge. Otherwise, it's going to keep rolling until it gets to the bottom, where again it's stable. Now you need to stretch your mind to think of stability as the idea of electricity. So these electrons are negative particles that are swirling around the outside of this atom. Those electric particles are in movement, constant movement, and they interact not just with other atoms, but they interact with the other electrons that's in the same shell as it has. So we're going to see that stability for an atom is not the idea of gravity, but it's the idea of electricity and the electrical stability of that atom. So if you can make a bond with another atom, the total energy of the atom is actually less, and atoms will tend to react together until the total energy is as low as it can get. When it's as low as it can get, that is called stable. So that's my picture here of the bottom of the hill. If you can get to where the atoms are bonding, then they have lower energy, and lower total energy is more stable, and an atom will tend to react until it's stable. Now let me try to explain why it's the octet. So I'm going to ask you to just look at the purple elements here on the periodic table. We have two columns that are purple. We have the first two columns, it's called representative main group elements, and the last 6 columns, which are also called representative main group elements. Okay, so what's happened is that the periodic table, which has all the elements in it, is giving you a lot of information, more than just the names of the elements, but basically how those elements interact, how many electrons they have in their outer shells, all kinds of things. So if you can extract from this the 2 and the last 6, the first 2 and the last 6, into 8 columns, then it's a little easier to see what I mean by octet. So here's an extraction from the periodic table. The first 2 columns were the first 2 columns on the periodic table that you saw that were purple. The last 6 are the last 6 columns that you saw that were purple. What we've done is we've removed the yellow section that we saw in the middle and the ones at the bottom and simply shoved them together into 8 columns. What you're going to see is that each of these 8 columns have one more valence electron. Starting in column 1, the 1A group, every one in that column, now I've only got the first 3 rows, but all of the ones in the periodic table, everyone in the first column is going to have everyone in the first column is going to have 1 valence electron. Now, they've got 3 shells here, so let me show you what I mean. In period 1, or in row 1, we've got the valence electron shown in red. Okay, so there's only 1 shell on the first row, so its valence electron is its only shell. And hydrogen would have 1, and then helium would have 2. Now it's filled. That entire shell is completely full as it can get. If more electrons are added as the elements get bigger, you're going to have to add another shell of electrons. So in row 2, you've got the black ones are the inside shell, okay, and then the red one shows the valence electron. Again, valence just means outside shell. So column 1 will have 1 in its outside shell, then 2, then 3, boron has 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, neon 8. Okay? When it is filled, it's going to go to the next shell. And so its valence shell will now be its third shell. So row 3 has a valence electron shell of the third shell, and it has, again, 1 through 8. So sodium having 1, argon having 8. Okay? So when I say octet rule, what I'm really meaning is that the row is filled, or the shell is filled. Once that shell is full, it's stable. And if you can get an element to have a full electron shell, then it is chemically or electrically lower in energy than it was as a regular element. So chemistry, essentially, the reactions in chemistry, is all of the detail work of trying to either share or steal or other ways of getting a full octet rule. So the octet rule normally means 8, because in row 2, a full shell has 8, in row 3, a full shell has 8, and you're going to see that in subsequent shells, the valence electrons are filled with 8. In the first row, it's a bit of an exception. It's filled with 2. So in the first shell, and only the first shell, helium has a full valence electron. So it's not an octet because it's full at 2, but that's an exception. You could say row 1 only needs a duet, and row 3 on would need an octet. Column 8 are called the noble gases, and I think the idea in mind here is nobility as in stuck up, nose in the air, looking down on everybody else who are not as good as they are. Noble meaning not, I wouldn't deal with you. So we don't really have nobility in America, I don't think. Nobody I've ever met was noble, but the idea that they would not deal with people less than them. And that's the idea here in chemistry. Anything in group 8 usually does not make compounds. they don't have to share electrons. They don't have to steal electrons. They don't have to do any funny business, because they already have a stable, full octet. And as such, they're very stable elements, and they don't react with anything because they don't need to react. That doesn't need to fall. The boulder doesn't need to fall because it's already at the bottom of the hill. So elements will go through three types of bonds. We're going to see that they either steal or get stolen from their electrons. That's going to be called ionic bonds. We'll look at that in a later lesson. They share electrons. That's called a covalent bond, where the valence electron is counting for both of the atoms in question. Or they have a situation like a metallic bond, where the valence electrons are actually along the outside of the entire metal, and that's why it's called a metallic bond. So we'll see that there's various ways that an atom can get an octet and become more stable than before. And these atoms are formed usually underground in high pressure, high temperature situations where it's forcing them to have the lowest energy possible. So let's review. Anything in column 1 is going to have 1. So if it needs 8, it's either going to need to share 7 with someone, that's unlikely. It's going to have to steal 7, which is unlikely. Or it's going to have to lose 1, which is more likely, and we'll see why later. So anything towards the end, say towards group 8 doesn't do anything because it's already stable. Group 7 usually will either share 1 or steal 1 so that it can become 8. Group 6 will steal 2 or share 2. Group 5 will steal 3 or share 3. Group 4 will steal 4 or share 4. Once you get into the lower sides, so like group 3, usually it's going to either share the 3 that it has, each one separately, or it's going to give up the 3 that it has. Because underneath those 3, if you were to take those 3 away, it has an inside shell that already is full. Okay, so if the inside shell becomes the outside shell because you've taken away the electrons in the outside shell, then there is already a stability. So on the left, you're going to tend to give away or share those electrons. On the right, you're going to tend to steal or share those electrons. And then a final review is that a bond is either a transfer, and I think of as stealing or getting stolen from, or a sharing of electrons that result in a full valence shell. So 2 in the case of the first, like hydrogen, in the case of the first period, you'll be full, or in all subsequent rows, you're going to have 8 required. And the 3 types of bonds are different ways that these elements can become more energetically stable. Ionic bonds steal and get stolen from. Covalent bonds share. And metallic bonds, all of the valence electrons go to the outside of the entire metal and can be conducted like electricity. That's what electricity is, the movement of electrons in the case of a copper wire or something like that.